So now we're going to look at measuring the change in internal energy for chemical reactions. So a system, it will exchange energy with its surroundings by heat and by work. So here's our heat, Q equals mc delta T, and the work we're referring to here is pressure volume work, negative P external delta V. So the heat could be going from system to surroundings or from surroundings to system, and the work could be going either way as well. So change in internal energy during a chemical reaction is a measure of all the heat that's exchanged with the surroundings. Heat and work. So delta E is equal to Q plus W. If we do this in a container that is at constant volume, we don't let the volume change, then the work is going to be zero because the change in volume is zero, right? So if work is zero, then we end up with delta E for the reaction is equal to Q, the heat. And we put a V down here to indicate we're talking about at constant volume. This does not apply all the time, but it applies at constant volume. A lot of chemical reactions occur in a solution. And how can you measure the change in energy or even the change in temperature for individual chemicals in a mixture? You just can't. And even things that don't occur in aqueous solution, it's still just, you just really can't do it, right? So what we do instead is we measure the change in temperature of the surroundings. So remember we put that block of copper into the water. It would be hard to take the temperature of the block of metal, right? Because you can't stick a thermometer into it, right? But you can stick a thermometer into the water being the surroundings, and you can learn about how much heat was gained or lost. So what we're doing here is we're going to measure the temperature change in the surroundings using something called a bomb calorimeter. It's insulated, and the surroundings then are very controlled. We don't let the volume change. So Q for the system, the reaction that we're looking at, will be equal and opposite in sign to Q for the surroundings. And here Q for the surroundings is the calorimeter. So calorimetry literally means measuring calories. It's a technique used to measure heats of reaction by looking at changes in temperature. So we've got a system, that's our reaction. It's going to exchange heat with the surroundings. We can observe the temperature change over here. So this is a schematic of a bomb calorimeter. They're usually made out of metal and very well insulated. Inside, there's water. We have a thermometer. We have a stirring mechanism. And then we have the bomb. So this is tightly sealed. It doesn't leak air, doesn't let water in, has a controlled volume. And we put the sample in here and put some oxygen in here, and then we light this on fire. This is actually how they measure calorie content in foods. There's an experiment that can be done in a student classroom where you burn a peanut and you figure out how many calories are in the peanut, right? So it's the same idea here. So we're going to measure the change in temperature of the calorimeter, which will be equal to the change in temperature of this water. We're assuming that no heat is escaping. We've got this well insulated. Of course, a tiny, tiny bit is going to escape, but it's small enough we can ignore that. So the heat gained by the calorimeter must be equal to the heat released by this reaction. So Q for the calorimeter we could define as the heat capacity of the calorimeter times the change in temperature we observed, and that's going to equal negative Q for the reaction. Because the volume is constant, Q reaction is equal to delta E for the reaction. Okay, let's do a problem. When 1.550 grams of liquid hexane undergoes combustion in a bomb calorimeter, the temperature rises from 25.87 degrees Celsius to 38.13 degrees Celsius. Find delta E reaction for the reaction in kilojoules per mole. The heat capacity of the bomb calorimeter determined in a separate experiment is 5.73 kilojoules per degree Celsius. Blah. Highlight the numbers. Figure out what they're asking us to do. They want delta E reaction. Okay, I'm going to write down my numbers. 1.550 grams and 25.87 degrees Celsius and 38.13 degrees Celsius and 5.73 kilojoules per degree Celsius. Well, we have two temperatures here, right? The temperature goes from this one to that one. So the 25 is the initial. The final is the 38. I think we're going to need a delta T. Yeah, probably. Let's just go ahead and calculate that. It's the final minus the initial. .13 minus 25.87. 12.26 degrees Celsius. So that's delta T. What could we label this? 5.73 kilojoules per degree Celsius. It tells us up here that's the heat capacity for the calorimeter. It doesn't say specific heat capacity, it just says heat capacity. So that's C without the S. Or referring to the calorimeter, we'll call it C-cal. So we were just looking at some relationships. We said that Q for the calorimeter was going to equal C for the calorimeter times the change in temperature. There's no M here because the calorimeter's mass is always the same. And C-cal is the mass times the specific heat capacity. So I know that's confusing, I'm sorry. And then, so delta E for the reaction is equal to Q for the reaction, which is equal to negative Q for the calorimeter. This part is telling us that the heat lost by the reaction is gained by the calorimeter. Heat can't be created or destroyed. Whatever's lost by this has to go somewhere. It's going over here. Q reaction is the change in energy for the reaction at constant volume because the pressure volume work was 0. So we need to calculate Q-cal then. right? So Q for the calorimeter equals the heat capacity of the calorimeter times the change in temperature. So that's 5.73 kilojoules per degree Celsius times 12.26 degrees Celsius. And those units cancel out and give us a unit of heat, kilojoules. Wrong line. 70.249 kilojoules. Q for the reaction equals negative Q for the calorimeter. So negative 70.249 kilojoules. Everybody okay with that? Is that the answer? Not quite. It's asking us for delta E in units of kilojoules per mole of hexane. So the amount of heat given off by this reaction depends on how much hexane was burned, right? A drop of gasoline versus a whole tank of gasoline, very different amount of heat given off. When we do kilojoules per mole, that's going to be constant, because if you have a bigger gas tank exploding, you have more moles, right? And so it'll give you more heat. So we need to see how many moles this represented. So we have that 1.55 grams that I just kind of left hanging up there. That is grams of hexane that burned, right? How many moles of hexane is that? I can use the molar mass to calculate that. So that's going to be 6 carbons times 12.01 plus 14 hydrogens. $86.172. It's the mass of 1 mole. Oops. Is that where the number goes? No. I wish I did that on purpose. I didn't. Didn't do that on purpose either. So 1 mole of hexane weighs 86 grams. So we have 1.55, so we're going to divide by 86.172. And this is going to give us 0.017987 moles. One, two, three, 4 sig figs. 4 sig figs. So I get Q, I get heat of this value for every this many moles that burn. It's this per that. So I'm going to divide, right? So delta E is going to equal my Q, that's kilojoules, divided by the number of moles. That were used in this particular experiment. That's the number of moles that gave that specific amount of heat. Negative 70.249 divided by the other thing. Kilojoules per mole. So if we want to indicate that we have three significant figures, our best option is to put this into scientific notation. So negative 3.9. I'm keeping this next one, the 0, but the next number is a 5, so I have to round this up to a 1. 3.91 times 10 to the, I'm moving the decimal point 1, 2, 3 places. Is 3,905 a big number or a small number? It's a big number, right? How would you feel about a check that was $3,905 that you could deposit in your account? I feel pretty good about that, right? So that tells us this is a big number. That means the exponent is positive. Yes, it's a negative number, but that negative is out here. Some of you are still getting a little mixed up when you convert between scientific notation and decimal notation. Your calculator can actually do that for you. So if you want me to show you, I'd be happy to do that. So that many kilojoules per mole. Any questions?